All right. Hi, and welcome everyone to exercise course number 7, where we will accordingly talk about exercise sheet number 7. We have for our topics the adaptive gradient methods and the hypergradient descent scheme, simply the hypergradient descent. And we want to start with a quick warm-up exercise, namely we want to show that in fact in the original paper of Adam, I think I have it here open somewhere. No, anymore. Not so important. So in the original paper, which suggested the Adam optimizer, there they provided an analysis of the Adam optimizer for a bit different scenario. I don't know whether you had a look at the original paper. I here gave the reference. It was in fact for an online convex optimization problem where your objective value function, to keep it simple, is varying in each iteration. But you can also have the simple assumption that the objective value function stays always the same, and you want then to optimize over all iterations, more or less. And even for this simpler case where the objective value function is always the same, and this is the scenario we have in fact here. So I translated their lemma. They had one lemma for this inequality they have. I have translated it into this scenario where you always have the same objective value function. And it's stating then the following. So if you sum up over capitalized T many iterations, the gradients of your so the gradients evaluated at your solutions for one specific component I, and divide that every time by the square root of the iteration number, then this left-hand side sum is always bounded by 2 times a constant which is in fact equal to the maximum value of the absolute values for the gradient at iteration t. This is also a bit questionable. I mean, this is the assumption they had, that they don't specify the t here in fact, but here on the left-hand side you have something which is iterating over the t. But well, this is not so drastic. I mean, you could also have a maximum over the t's, and then you multiply this constant with the Euclidean norm of the vector g1 till capitalized T I, which is nothing else than the history of gradients you had for their specific ith position. This is what you see here. The first gradient, or second rather, and its ith component then in the second iteration till you get to the tth iteration. And already this inequality is not true. There are other inequalities, in fact, in the proof of Adams, which are not true, but it's already breaking down here. So it was simply too easy, the proof which they gave, and we will show here why it's not true what they are stating here in fact. And it's in fact really simple how you can construct a counterexample. Simply take the case that assume, for instance, you have a linear function, objective value function, such that the gradients is in fact nothing else than, for every iteration, it's simply the vector consisting of 1/2. This would be the case, for instance, if you have 1/2 times t or something like that. Yes. 1/2 times theta, no, not t, 1/2 times theta. And well, then the objective value function won't change. The gradient will be the same every time for each of your iterations. And we can have a look at the case that we only have 5 iterations. What happens then? Well, this historical vector, which consists of all these components, well, we have here, when we compute the Euclidean norm of that, we are summing up the squares of its components. But each of its components, if this is our gradient for each iteration, is 1/2. So here we are summing up every time a 1/2 squared. We do this 5 times, so t is 5. So what we have, in fact, is 5 times 1/2 squared, which is the same, 1/2 squared, and then taking the square root is 1/2 times square root 5. And what do we get for this constant g infinity? Well, the gradients are in each component 1/2. What's the maximum of that? It's 1/2. So let's have a look at this left-hand side. The left-hand side is here. We have here every time a 1/2, which is not depending on the iteration index t, so we can also write it in front of that, which is here. We have that our total iteration number is 5. We are summing up 1 over square root t, which is greater than 3/2. Well, I haven't given a real good reason for that, but this is the case, so simply because 1 plus 1 square root 2 square root 3 square root 4 and so on. If you look at this sum, this will be a bit greater than 3. It's something like 3.2 or something. I mean, it's just a counterexample. You can also play around with the numbers, but this is doing already what you want. So this sum here is strictly greater than 3/2 because the sum here is greater 3. 3/2 in turn is strictly greater than the square root of 5 divided by 2. What is the square root of 5 divided by 2? So we can first of all add or multiply it with a 1. We take this one here. This is a 1 which we multiply to that. And why did we do this? Well, because this 1/2 here is in fact our g infinity. And we have seen above, this is here. We have seen above that 1/2 times square root 5, this is the Euclidean norm of this history vector, and well, the 2 is what we had before. And what we have is this orange left-hand side is strictly greater than this rainbow color right-hand side. This is what we had here. So, simple example, this is not true, what they are claiming. And Unfortunately, this is always the case, or most of the time the case, when you have a very complicated proof which is relying on lemmata and so on. Once one of the lemmata is wrong, you have a problem. Yeah? So your entire proof breaks down. And as I said, it took a while after the proposal of Adam that the bug has been fixed a bit differently. So one variant I showed you in the lecture with this more or less very complicated assumption we had. Yeah, this is how you can fix the convergence issue of the Adam optimizer. All right, then this was our short warm-up. Now what we want to do is we want to show a similar result which we have not showed but stated, let's put it like that, stated for the adaptive gradient methods, which were a result of the big assumption we had. So for the adaptive gradient methods, we had these essentially free assumptions, and then you arrived at some statement which is telling us that the minimum gradient we see, or the minimum Euclidean norm we see for the adaptive gradient methods, is bounded by some term which is going down to 0 with the iteration number. And in the lecture, I said that you can also show quite easily something similar for the gradient descent, although this result already implied also the case gradient for the gradient descent. But for the gradient descent, you have a more easier to interpret result where you don't have to worry about other things. And this is what we want to do now. So we want to show a similar result for the gradient descent when we have smooth objective functions. Not necessarily convex. This is not needed here. We don't need a convex objective function. Only has to be smooth. And the beta smoothness, not the coordinate-wise beta smoothness as we had it today, but the classical beta smoothness. Although you can also look at the case for coordinate-wise beta smoothness, but this is another story. All right, so we know by now that the theoretically optimal step size in such a case, when we deal with a beta smooth objective function, the optimal step size is a fixed step size, a constant step size, and it's simply 1 over the smoothness parameter beta. And we divide what we want to show into 3 parts, A, B, C, and we start with part A, where we have the following very similar result we had today in the lecture, in fact, where we show that the decrease in the objective value function via the gradient descent is something. So we have here on the left-hand side the objective value at the new iteration, and this is always smaller than or equal than the objective value at the previous iteration minus something which is non-negative. Here again, you have something non-negative, and if you compare it with what we had today in the lecture, it's quite similar. The only difference is, of course, here that this is depending on the full gradient. Today in the lecture, it was depending on the partial gradient because we had this more fine-grained coordinate-wise beta smoothness. All right, so enough of that. Let's see how we can show this. Quite similar to what we did today. We start with the definition of beta smoothness. What is again definition or one implication of beta smoothness, rather, because we have not convexity assumed, we only have beta smoothness. But if it's beta smooth, then our usual way how we specify beta smoothness is the function f is always bounded from above by this quadratic function, yeah, which is resembling more or less the second Taylor approximation. Not necessarily exactly, but it's quite similar if we would have as the Hessian matrix a diagonal matrix. Yeah. Again, I only can reiterate myself again and again when I talk about beta smoothness. You have here on the right-hand side, you have a cup which you can put inside the function f at every point at the bowl in that cup. The bowl is untouched by the function f. And again, this is also something you can require and can also be fulfilled for functions which are not convex necessarily. Of course, you can have bumps where the convexity is violated, and then this is still true. All right, then how can we use this beta smoothness function to get to our result we want? Well, we use the following substitution. Theta prime is theta plus 1, because this is the left-hand side which we want for our result. We use for theta here and here theta t, because, well, it appears here. So it's a rather good idea to do this. And of course, let theta t plus 1. So far, so good. What can we say more about this resulting inequality which we get from beta smoothness? Well, there's a relationship between the thetas for subsequent thetas for the gradient descent, and the relationship is, you know it by heart right now. Next iteration is given by previous iteration subtracted by gradient evaluated at the current iteration with step size gamma. And the step size we use is 1 over beta. Yeah? This is what we have here. So plugging this in, what do we get? So the left-hand side with the theta plus 1 stays the same. This is how we want it. The theta t is here also untouched. But then, if we look at this here, what do we have? It's telling us theta t plus 1 minus theta t. This is minus 1 over beta times the gradient at theta t. Yeah. So this thing here is exactly this here. Also the same here. Yeah, okay, I have here. The minus is in fact not true, but doesn't matter, we have it in a norm. Yeah, this is what we get exactly here. And if we now consider that we have here the inner product of the gradient, the transpose of the gradient, here we have the gradient as it is, so we have the inner product of the gradient with itself, and this is then nothing else than the squared gradient. The scalar can be, of course, written in front of that. Here, for the second term, what do we have here? We have that the beta from the squared Euclidean norm is coming out as a beta square. So it's canceling out the 1 in the enumerator, and you're left with 1 beta in the denominator. And, well, the resulting equality, so this is an equality what you get here, can be rewritten by simply realizing we have here and here, of course, the same terms with different coefficients. And combining the two coefficients, you get as a coefficient for that 1 over 2 times beta. And this is exactly what we wanted to show, right? So the decrease we have is specified by at least the squared gradient norm at our current iteration multiplied by 1 over 2 beta. This is what we have wanted to show. All right, then from this, we go to our next step, namely showing that when we sum over the gradients, squared gradients, here's the 2 missing, but well, if we don't specify it, we simply agree that we are talking about the Euclidean norm. If we sum over the squared gradients until some iteration number t, then this here is bounded from above by 2 times beta, and then the difference we have from the starting position and the minimum value we have for the function, for our objective value function f. Okay, so this is what we showed in A. Now this is what A was showing, which holds for every iteration number t. Yeah, so we haven't specified the t here, but due to this relationship which holds for every t, this is also true for every t. Okay, so we rearrange it. What do we rearrange? Well, we bring this here on the right-hand side. We bring this here on the left-hand side. We multiply the entire inequality by 2 times beta, and what do we get? Exactly this here. No? Squared gradient is on the right-hand side. F theta t plus 1 is on the right-hand side. The difference between the two, which is multiplied with this 2 times beta. Okay, so we have this, and we are interested in summing this thing here up. So let's sum this up. We are summing this up using, can I have it on 1? Yeah, we are summing this up, and we can use it in every iteration that, or in every summand that this inequality is true, because this is holding for every t. We plug this simply in for the summands in the inequality. We only make it larger or equal if we do this. And then what do we get? We have here a telescoping sum, right? So this is 2 times beta, and then also the 2 times beta can be written in front of the sum. And what do we get here? We have f theta 0 minus f theta 1 plus f theta 1, and you know what's happening right now, minus f theta 2 plus f theta 2, and so on, until we have here plus f theta t minus 1, where we also have here, we have here f theta t minus 1, and then the very last summand is plus f theta t minus 1 minus f theta t. And this is what you get here. So cancel, cancel, cancel. What is left is this and this. And okay, typo 0. This is what you get here. Okay, and what can we say? So this is an equality, of course. And what can we say now about this term in violet? Well, it holds that the infimum of the objective value function is definitely smaller or perhaps equal to objective value at theta t. So we subtract here something bigger tangentially. So if we replace it here with an infimum, we subtract something smaller tangentially. So if we replace it here with the infimum, you get a smaller than or equal relationship. And this is what we wanted. Then from that, from this inequality which we wanted to show in B, this is exactly the part B, we want now to conclude more or less the counterpart, the same thing we had for the adaptive gradient methods, which was a bit more complicated with all these assumptions. Where we have now also the minimal squared Euclidean gradient. We see along the iteration is bounded by the error we have in the very first iteration, and it's linearly decreasing with the iteration number, the squared Euclidean norm. And this is a good result because, well, it's stating that at some point we are converging to some critical point where the gradient is 0. In the best case, it's a global minimum which we want to have. In a bad case, we end up with a local minimum, but this is something you cannot avoid if you don't have convexity or something like that. But of course, you have different tricks to avoid that in such cases. All right, how can we show this? Well, this is the part B, what we have just shown in part B. And well, if we now take the minimum over all summands, then what do we get? We get here that this here is smaller than or equal sum, and now I'm a bit lazy. And this is smaller than or equal than the minimum we have here. And this minimum is then not depending on the iteration number. It's one fixed value, which we can write in front of the sum. Then we are summing up t times, capitalized T times the same value, or a 1 more or less, and you get immediately this here. Also, this here is equal to what you have here. So this blue one is smaller than or equal the right-hand side we have here, which is still the right-hand side here in the display below. Now we divide on both sides with the t, and we have the result. If we now divide here with a t, we have this here. All right, now so you see also for non-convex cases you can get some kind of guarantee. It's not as good as in the case where you have convexity, but well, there's a price to pay if you drop convexity, because you cannot guarantee in the worst case that you don't end up in a local minima. This is only the case when you have convexity or something similar like convexity, quasi-convexity perhaps. All right, then, also keeping an eye on the time, we continue with exercise number 3, where we want to show one statement I gave in the lecture regarding the smoothness of the objective function which we have in hypergradient. So you remember what hypergradient is? The idea is simply to look at the choice of the step size in each iteration as yet again an optimization problem, which you can in turn solve with an optimization method. And to keep things simple, you can go with the gradient descent, yeah, and do a gradient descent regarding the choice of the step size. And the concrete objective function you have is specified here for the accelerated gradient descent. So in general, your objective value function is something, of course, it's also, you can also make it coordinate-wise dependent, but let's keep things simple. It's something like theta t plus 1, where the theta t plus 1 depends somehow on the gamma, on the step size. And it can depend on the step size in different ways, or let's keep it like different ways. The gradient descent way is that you have here f theta t minus gamma gradient f theta t. This is for the plane gradient descent. Or this is now what we will look at. It's the accelerated gradient descent, where instead of the theta t's, you have these look ahead steps with the yt's replacing the theta t. But the overall structure is quite simple, similar. So you want to every time optimize the objective value function with respect to the step size when you do an iteration. This is the overall idea of the hypergradient. So we recall here the accelerated gradient descent by Nesterov. And one statement we had, or which I gave in the lecture, was that the objective value function you see here, the g, this is a beta times squared gradient of the yt, of this look ahead step or look ahead point in accelerated gradient descent smooth function. And so we can also give a similar statement for the objective value function. So this is a side remark for the case where we have the plane gradient descent. We can have here a similar remark, namely that g is in fact beta times, not gradients of y, of course, but then simply y of theta t squared smooth. Because it's more or less coming from that one. All right, but let's consider the case for accelerated gradient descent. Let's recall what the hypergradient is. The hypergradient is nothing else than the gradient of the objective value or objective function which the hypergradient considers. The objective function which is considered by the hypergradient is here, this green, in green, the function g of gamma. And this is a univariate function because the gamma step size is a univariate value. It's a real valued number which you want to find. So don't overcomplicate it, but you can also write it here as the gradient with respect to gamma, which is nothing else than the partial or the derivative of the function g with respect to gamma. All right, then simply recalling what we had, the g, by definition, is f of theta t plus 1. This is for short. We are looking at the accelerated gradient descent. So this thing here is in fact this, which we already used here in g gamma. And well, how can we compute this derivative here? we use here chain rule, where we get the gradient with respect to this outer function times evaluated at inner function. The inner function is what we see here in red, which is nothing else than theta t plus 1. And we have to multiply it with derivative of the inner function. Derivative of the inner function is what you see here. Yeah? Partial derivative of inner function with respect to gamma. The inner function is quite easy to compute the derivative for the inner function, because it's a linear function where what remains from there is only the gradient, or minus the gradient, evaluated at yt. This is what you see here. And now this is important to note. Yeah, so we ended in the lecture more or less with the case that, well, this is the hypergradient, yeah? Simply the inner product of the gradient evaluated at the next iteration and minus the gradient at the look ahead iteration step before. But there's a dependency on the gamma. Yeah? This is the important thing, namely here in the theta t plus 1, because we can also write out the theta t plus 1, and the theta t plus 1 is having here a dependency on the gamma. No? So you have here still a dependency on the gamma. So to stress this a bit more, we can also change here the name of the parameter, the input parameter, perhaps gamma prime. Yeah? Let's call it gamma prime and consider the derivative. You get exactly the same, with the only difference that you have here a gamma prime instead of the gamma. You simply have renamed it. But this is, again, important to make clear where the dependency of this derivative is with respect to the input parameter. And here, exactly at this yellow spot there, you have the dependency. And what we need to show is that this gradient, which is nothing else than this ordinary first derivative in the univariate case, that this thing here is a Lipschitz continuous function, because this is how we specified, how we defined smoothness in the first place. And with the right Lipschitz constant we have, so this beta times squared gradient thing. And recall what Lipschitz continuous is telling you. So F is L Lipschitz if and if you have Fx minus Fy is smaller than L times the difference between x and y. This is true for every x and y in your domain, in the domain of the F. Let's say it's Rd. Now substituting the F with the hypergradient, which is nothing else than the gradient of this function g, for two different values, for some arbitrary two different values, which are real valued numbers. This is the input. There we have to show that we get at the end a similar inequality as here, where the L, where this L here is exactly this constant. We have only here an easier case, because here this clean norm is overdue, because we only assume that our function f is mapping to real numbers. But here the distance might be a Euclidean norm. But our function g yeah, which we will, or gradient of G, which we'll use for the F, yeah, to show the Lipschitz continuous property. This is a univariate function where we need to have at the end the difference between, the absolute difference between the input, yeah, the gamma and the gamma prime. All right, how can we show this? Yeah, gradient, as we saw before, nothing else than the ordinary first derivative. We have computed the ordinary first derivative. Namely, we have it here. This here is this thing. And for illustration purposes, we have also said, well, if we replace the gamma with a gamma prime, with the different value we plug in, then we get almost the same where the gamma is replaced with a gamma prime. All right, simply plugging in definitions. And now we only have to look at this term in cyan and pink, or pink, rose, I don't know, some red color, more closely. And what do we see there? We see here and here the same terms, right? So we can use the law of distributivity and have it here on the right-hand side, and we collect this term minus this term to one bracket. This is what you get here. It's immediately visible, and here with the minus you have it as well. And now, what do we have here? We have here inner product, that's here in this green bracket in the last line, inner product of some term, which is a d-dimensional term. And here, the inner product of that with some other d-dimensional term, namely the gradient evaluated at yt. And we had a hint for this exercise sheet, namely that you should use the Cauchy-Schwarz inequality, and this is exactly the place where you should use it, because now what you have here is the x is what is in the green bracket, the y is what you have here in the black box, and the inner product of any x and y's, doesn't matter what they are in absolute value terms, is smaller than or equal than the product of the Euclidean norms of these two vectors respectively. So you get this one here, and we get the y, the Euclidean norm of the y here. Okay. And now, how can we continue from there? So you see, okay, somehow we need to use the beta smoothness assumption. So somewhere the beta smoothness assumption of the function f should come into play. The beta smoothness assumption is that the gradient of f is beta Lipschitz continuous. You see it here again. The Lipschitz continuous assumption is what we just had revisited before, only with the difference now that the gradient is now a multivariate function. So therefore we have here indeed the Euclidean distance between the two. And it's stating the Euclidean distance of the function, which is the gradient of f, evaluated at two different points, is always bounded from above by beta times the difference between their Euclidean distance inputs, the Euclidean distance between their inputs. And this holds for every theta and theta prime. Okay, this is good news. If we look a bit closely, here we have the gradient of f evaluated at this point, yt minus gamma gradient f of yt. This is what we can use for the theta. And here we have again the gradient of f at some other point, namely at the same, only with the gamma replaced by gamma prime. So you can, and this is where we, so this is where we ended. We can use this here, exactly here at this position, this point, and we get, well, the Euclidean distance between the gradient of f evaluated at exactly these points, the yellow, the violet and this rose point. This is the violet point. This is the rose point. And we have to multiply it with the beta, this Euclidean distance between the two. Now again, simplifying the things, this yt, oops, this yt is cancelling out. This yt, we have here 2 times the same term, namely the gradient of f evaluated at yt, multiplied with gamma minus gamma prime. This thing here can be written in front of the Euclidean norm because this is a scalar, gamma minus gamma prime. These are scalar values. You can write it in front of the norm as an absolute value. And what remains is then the norm of the gradient of f at yt times that thing, so you have it as a squared. So what we have at the end is exactly what we wanted to show. The difference of the hypergradient, evaluated at 2 different points, gamma and gamma prime, is bounded from above by the seeked Lipschitz constant, or the claimed Lipschitz constant, which you see here, times the distance between the input values, gamma and gamma prime. And, well, this is what we wanted. All right. So far, so good. And as I said, you can do exactly the same argumentation for the case to show that if you use the gradient descent as the underlying gradient-based method, that the objective value which you are optimizing with the hypergradient is still beta smooth, only here the term in the squared gradient is a bit different. That's the theta t instead of the yt. Okay, good. Then I would say we go to the practical exercise unless there are questions. All right. Maybe in Zoom chat. Oh yeah. I know that's me. I thought that I'm also counted. All right, then. Oh, so plenty of time, actually. Yeah. Oh, better not. I'm not the best programmer. At least not in Python. In R it's better. By the way, so Python is preferred, right? So I asked this, I guess. Yeah.
rely on like one exercise on your bachelor rather than one
Mm. Yeah. This is, I guess, the case for most of students. Yeah, but this is not freely available. So there are free versions or variants, but like this.
We have licenses now.
Ah, okay.
Yeah, it was like, yeah, you get to know that software. In the consensus was, yeah, most of them see Python, so just Python.
Yeah, okay. All right. Yeah, good. Then it's good that we have chosen Python. All right. So what we want to do is, again, we look at our running example for the practical exercise of least square estimation. You know it by now. We have this feature matrix X where we store the features. We have some label vector and some target values, more or less. And what we want to find is some good relationship between how we can explain with the X what the corresponding Y is. And one way to do this is in a linear way, now that you find some weight vector which you multiply with the X such that it's coming close to the corresponding Y. And you do this for all of your pairs of X and Ys you have. And you have n many of them. And this is nothing else than the least square estimation, what's known in statistics and also in machine learning. And we have now used a couple of methods to solve this: plane gradient descent, accelerated gradient descent. Both are still there, and now we also want to have a look at the 3 new algorithms we introduced last week, namely Adagrad, RMS prop, and Adam. In fact, I have left out RMS prop because it's in fact a special case of Adam. Yeah, if you set the momentum term or the decay rate for the momentum term to 0, you have RMS prop, which is in general, or I would say it's safe to say that Adam is performing better than RMS prop in general. Perhaps you can construct some specific scenarios where this is not the case, but in most cases it will be the case that Adam is way better. All right, so as usual, we load our helping functions. We load our data with the height and weights, where I still cannot remember what was. So we want to predict the weight via the height. Yeah, this is how we do this. Although it's perhaps better the other way around, but well, doesn't matter so much. We have 10,000 samples. The dimension is 2 because we have these dummy features, yeah, where we have all ones in one column. We compute the objective value, yeah, with the convention that we plug in here an x theta y, which is x times theta, yeah, in matrix vector multiplication, and then subtracting the y. Yeah, so exactly this thing we see in the objective value function here. So all we need to do to get the objective value function is then to compute the Euclidean squared norm of this thing and divide it by 2 times n. And this is what we do here. Yeah, so computing the mean when we square up all the entries and dividing them by 1/2 is doing exactly what we want here to have the squared Euclidean norm. Then we have these functions to calculate the smoothness constant beta and also the strong convexity constant alpha. Yeah, very similar. I explained it in the last time, where for the beta we have the maximum eigenvalue of the matrix of X transposed X, and then divide it by the number of observations. Yeah, so Y shape 0 gives you the N, the big N. And for the alpha, for the strong convexity, yeah, quite intuitively, you have here the minimum eigenvalue of the same matrix, and you still divide here with the number of N. Then the Lipschitz constant for this objective value function, we also calculated this a couple of times before. We need the gradient, of course, the gradient for our objective value, which is given here. And we define the function such that we get the gradient, and also, because we need it nevertheless, why we compute the gradient, exactly this x, theta, y vector, which we get when we multiply the matrix X in a matrix vector multiplication manner with the theta and then subtract the y. And so we get then two arguments back, the gradient of that thing and x, theta, y. Then this is the old gradient descent version, which we can actually delete. I don't know why I keep it here. Because what we did last time was we specified the accelerated gradient descent method with the help of the gradient descent function we had before, simply by having here a functional parameter momentum, yeah, which can be turned off, which is by default the case, yeah, that you have here always a 0 returned, so that you don't have the alpha set to something and the accelerated gradient descent boils down to the plane gradient descent. If you do here some momentum calculation, yeah, then you have to specify a momentum function, which is returning for the current iteration number what the momentum coefficient should be, yeah, the alpha t plus 1. All right. The gradient descent, or the accelerated gradient descent, as it rather, stores a couple of things. All the thetas you will see during the iteration. Of course, it's already including the initial theta. It's storing all objective values you will see. And then it will update the theta, and the previous theta will be stored to make the iteration. Both are initialized as the initial theta for implementation purposes. The v is in fact the y, because the y is already reserved. So by the labels or the target values in the regression problem. So think of the v as the y. And we do then the iteration. We start by always the other way around, so to speak. Yeah, so we first update the v, if we do this in this way, and have the theta and the theta pref as the same value, then this is indeed the iteration procedure you have here, where you have the update of the theta plus 1, and then you update the yt. We compute the gradients with our compute gradient function. We get the gradient, we get this x theta y vector, yeah, which is x times theta minus y, which we plug into the calculate objective function. This is the convention we use to get the objective value. The previous theta is now the theta we have right now, and we update the theta by means of the rule of the accelerated gradient descent, which again, if the momentum function is the 0 function, yeah, this here is a 0, the v is a theta, and this is then exactly the case, yeah, exactly the same as doing a plane gradient descent. We store, we collect the thetas, we store and collect the objective values, and give a print here to see what is going on. All right. Adagrad. What is Adagrad doing? Yeah, well, the overall procedure is similar. The only difference is that we have to do, a calculation or a division component-wise. And the division we are doing is specified by these terms you see here, epsilon plus the square root of some specific value which is stored in a vector st. And what is this vector st? This is nothing else than the sum of the squared gradient terms for the corresponding component I. Yeah, so you have it for each I. And this is also very good. That simply to decrease the step size for components where you have high gradients, where you don't need large step sizes, and make it tendentially large for those where the gradients are small. Well, we specify this under a new function Adagrad. We could also implement it under one framework, in fact, but perhaps something for next time. And the general scheme is quite similar as before. The only new component is now this S vector storing the squared gradient sums, but the iteration as before. Compute here gradients, the x, theta, y, the objective value. You update now this S by adding to it every time the squared gradient, because this is exactly what is new in every iteration, that you get a new squared gradient. You can conveniently do like this in Python. And you update the theta in the Adagrad manner, in the sense that theta is minus the baseline step size, this gamma which is appearing here, for which you can play around as you want. It's again a functional parameter as we had it before. You multiply here with the gradient, and thanks to the component-wise definition or comprehension rather from Python, component-wise comprehension, if you divide vector by a vector, it's doing exactly the component-wise division, multiplication, however you want it. We want here the division. Here you have a vector, or a list, is it rather, a NumPy array to be more precise, for which you apply the square root component-wise. You add to it an epsilon, which is a scalar, but list comprehension of NumPy array will add the epsilon to each of the components. You divide it here with or the grad vector you have here, or NumPy array. You divide it with another NumPy array, and you do this then component-wise. Exactly how we would like it.
Close to zero, but not zero.
Yeah, so we have used here some of these typical default values. You can also choose here something you would like, but it should be quite small. Yeah, not dividing by zero. This is the only requirement you need to fulfill. All right, then Adagrad. This was Adagrad. What about RMS-prop and Adam? As I said, RMS-prop is in fact a special case of Adam. So let's recall Adam. Adam has the following scheme, iteration procedure, concrete one, where you don't have the gradients anymore. Here you don't have the gradients as before, but you have here, in fact, some momentum term, which is nothing else than a Desaying average of the past gradients. And the Desay rate is specified by alpha. If you set it to 0, this Desay rate alpha, what you get here is that the Vt is corresponding exactly to the gradient of theta t, and this is then what you have in RMS prop. The difference from to Adagrad of RMS prop and Adam is in this vector st you have here. So it's almost the same average of the squared gradients, yeah, so exponentially is saying average of the past squared gradients you have, almost, because you have here also some bias correction, yeah, so this s tilde t, what you see here, is exactly an exponential descending average of the past squared gradients. Now you see it here. But this is then divided by 1 minus c over t, which is then correcting for a bias. You also do something similar for the momentum term. So in the typical formulation of the atom, you also have a v tilde term and a vt term. I preferred it like this, so that you have here the vt, which is then divided by 1 minus alpha. Okay, and for Adam, we also specify a new object or a new function. Again, we could, in fact, store everything into one framework. Perhaps we do this next time. Not so important right now. So we have here this alpha descending rate, this c descending rate with the default parameters suggested by the Adam people. Essentially very similar what we did here for the Adagrad is also useful for the Adam. So what is new here is that we have also this momentum term additionally to the S term, which we update here using this update procedure, more or less what we see here. Okay, then let's see how these adaptive gradient methods perform for this simple least square estimation task. I forgot to, oops. The gradient. So gradient descent, we saw this now a couple of times. You can also show this graphically, accelerated gradient descent. And now we look at the Adagrad methods, the adaptive gradient methods, and start with Adagrad. And what we see for Adagrad, so we choose for the base gamma, the base step size, also the same 0.3 should it be, but this won't change that much. We use the same naive constant step size as before. Look at the Adagrad objective values, and what do we see? A quite slow convergence. Yeah? So we start with 2,700, and after 50 iterations we are at 2,400. For comparison, accelerated gradient descent starts essentially at the same. After one iteration, it's by 1,000, and so on. And then it's 15. Okay. Seems like Adagrad is indeed not the best one. What about Adam? Perhaps Adam is doing better. But Adam is not much better. Yeah? So you have here, after 50 iterations, essentially only, but you get almost, or you're not as close as to accelerated gradient descent after 2 iterations. Let's see, perhaps this was due to the choice of the gamma. So let's see what we get if we use the step size choice by incorporating the Lipschitz continuity. Again, plane gradient descent converges quite quickly, let's say. Accelerated gradient descent, where we have this momentum coefficient specified by this recursive lambda sequence, is converging also quite quickly. What is Adagrad doing for this Lipschitz choice? Well, not much, let's say. Yeah, so you see the values here are not better than for the naive choice. What about Adam? Is Adam better in this regard? And we see, well, not really. Perhaps we get also very good results if we choose the step size as if we would tackle a gamma well condition function, which we have, because there we know from theory the best step size is a constant step size, and it's given by 1 over the beta smoothness parameter. For plane gradient descent, this is perfect. So only one iteration and nothing happens anymore. So you're more or less done. Accelerated gradient descent, where the momentum coefficient is then a bit different than before, not depending on the lambda sequence, but now this is where we needed to calculate alpha, this alpha strongly convexity parameter. The same here, one iteration, you're done. Adagrad, using also 1 over beta. So you see, I don't tell you something different. A bit better to what we see before, but not as close as good as the others. Adam, same, well conditioned, gamma well conditioned. All the rest is by default. Better, way better than before, but still room for improvement. And if we plot everything together into one figure, so you can imagine the lines here above. These are the adaptive gradient methods. These are the accelerated gradient descent at the plane gradient descent. Accelerated is the dashed one. Solid one is the plane gradient descent. No competition. This is not unusual, let's say, because in fact our objective value function we have here is very simple. It's a quadratic function, not high dimensional, 2 dimensions, a lot of samples, and there a plane gradient descent is already quite doing the job, and the adaptive gradient methods are too complicated even in this case. So we could, so this is perhaps painting now a wrong picture. We could, of course, tune the parameters of Adam and Adagrad to have here a better convergence. For instance, so what is it's 0.1 already. I guess if you choose something bigger, the convergence is higher. If you okay, so here you have some alternating behavior, and well, choosing a base step size of 4 is debatable, but you see where this is going. If you play around with the base step size, you can get better, and definitely if you play around with the decay rates, which we haven't done here, we use the default alpha and the default C, which was in the implementation. Perhaps if we choose for C, I don't know, 0.1. Yeah, it was right here, right? Oh, yeah, sure, yeah, here. Not that good. Perhaps the 4 is a bit better. Yeah, exactly. This is a complete parameter search problem where you can play around with the alpha and the C. Yeah, you make it worse or bad. But the point is, very simple problem. The simple algorithm already does the job. And there are complicated, more complicated algorithms where you have to choose also tuning parameters or hyperparameters. Yeah, perhaps you should rethink that. If you have a more complicated optimization problem, yeah, then, which you usually have in training deep neural networks, where Adam or variants of Adam are the standard, the state of the art. This is another story. Yeah? There you have a quite complicated optimization problem, high-dimensional, non-smooth and such things. Here you have a very smooth objective function. It's a quadratic objective function, very smooth, well-conditioned. Yeah? Training neural networks is by far not well-conditioned, so there's nothing well-conditioned there. And for these cases, these more sophisticated adaptive gradient methods are designed more or less, exactly for such cases. So we can also have a look at the case with more complex data, where we have this concrete data set, and skip fast forward to what will be the result. Here you see, compared to the plain or the more simpler gradient-based methods, these adaptive gradient methods are not that bad. Yeah. So for instance, Adagrad is here this pointed line. Yeah. Red, green, and blue is here, and Adagrad has here the line where you have some dots from now and then after a line. And there you see, well, Adam with smoothness choice is, not that bad. It's still worse than accelerated gradient descent. Yeah, this is the dashed line with smoothness choice. It's the best here. Also, gradient descent with smoothness choice is also quite doing good. It's hidden a bit here with the blue dashed line, which is the accelerated gradient descent with constant step size. But you see now there's not a huge gap anymore as in the first case where we had this height weight scenario with only 2 dimensions. Now we have 10 dimensions, was it, or 8? In the concrete, how many?
Input dimensions?
The feature dimension was 8. 8 was it? Yeah, a bit more complicated, 10,000, 30, but still the objective value function is quite simple. It's still a linear model what you fit there, in fact, so hyperplane. Still, it's well conditioned and such things, so your plane gradient descent, perhaps with the momentum term, does the job. But things change in general when you have more complicated things, training deep neural networks, such things. So this is the main takeaway message from this practical exercise here. Any questions? Points to discuss, of course, also.
Maybe in the Zoom chat.
Perhaps. All right, so yeah, a bit earlier, but well, more time to enjoy the weather, right? All right, then thanks for participating, for watching. See you next week. Bye-bye.